Great, thanks. Thanks to the organizers for the kind invitation to come to this very special intellectual meeting in a very special place. I'm going to talk about dark matter, dark energy. I definitely belong to the camp of cosmology with small c. But I find myself, as one spends many years doing these big surveys, that there's no escape by trying to place it in the bigger picture. So what I'd like to do is to sort of share with you some thoughts as a humble astronomer, observational cosmologist, which may hopefully resonate with some of the issues which are of interest to this audience. Thanks to collaborators, we tend to collaborate with many people these days. On the left, it's my cosmology team at University College London. On the right, Dark Energy Survey, which has kind of dominated my research over the past 10 years or so, scientists from 6 countries. Lots of discussions, mainly technical, but they will also are relevant to what I'm going to say. And if time permits, I'll also comment about what it's like working in a big collaboration, the sociological, anthropological sides of it. So that's the outline. This is actually an extended version of a talk, the Gerald Widrow lecture I gave at the National Astronomy meeting in Portsmouth in June. And I have to say, it's kind of an excuse to think outside what Simon referred to yesterday as the comfort zone. So it's kind of a bit strange that usually in the typical cosmology conference, there's no chance to talk about what do you really think about it, and what are the issues. You have to wait until you make it to the pub to actually talk about these things. So it's kind of nice that this named lecture and also this forum allows me to say a few things, to share them with you. So I'll just give this again, keeping in mind that philosophers may not be familiar with the technicalities, especially those who may see it on the video. I'm going to review the status of dark matter, dark energy as of 2014. I would like to make some historical remarks. I know this is a meeting about philosophy, but I think the history of the subject is very relevant, and to kind of try to give you a flavor of how the paradigm actually shifted towards dark energy. And then to go even further back in time, have we been here before? I'll indicate that actually Newton already talked about the linear force in Principia. And I'll bring up the example of Neptune and Mercury in our own solar system, which nicely contrast the same conceptual issues we are facing today, namely, is there dark energy there, or should we tweak general relativity? And then, time permitting, I'll move a bit more into anthropology, maybe, and try to criticize, actually, the globalization that perhaps we talk to each other too much. Don't leave the meeting, of course. I'd like to talk to you. But maybe we over-interact, and this leads to a dogma. And finally, again, being part of a big collaboration and running the science program of the Dark Energy Survey, I could not resist thinking a bit about what's the cognitive limit we have to actually the size of a collaboration. How many people can we actually interact with? So it's a mixed bag, not the sort of things I usually talk about. So forgive me if I'm indeed stepping out of my comfort zone. Well, at the beginning, I happen to know how to read it in Hebrew, but it's just interesting that all these big questions and concepts have been around, and whatever language you speak, I think it's quite remarkable that concepts such as darkness, light, chaos appear there. Doesn't matter the context, but the actual concepts are there, and we're still struggling with those concepts. The dark matter problem is well known. I think it's most dramatically illustrated using those spiral galaxies. They rotate. For example, the sun goes around the center of the Milky Way at 220 kilometers per second. And the big surprise, this goes back to the 70s, is that when you plot the velocity against distance, there's a rise, and naively you'd think it would drop because most of the light is there, and hopefully maybe most of the mass is there, but instead the big surprise is that those rotation curves are flat, and this is given, basically is regarded as the main indication there is actually a dark, massive halo. But it has to be said, as we still have not found dark matter candidates in the lab, at least in principle, there's still the possibility that this flatness of rotation curves might be due to dark halos, but might be also due to modified gravity. There are theories by Bekenstein and earlier by Milgrom, Mond, that suggest it. Okay, so we're still in that situation that there is a discrepancy, and that's the key point of this lecture. There's a discrepancy between a relatively precise measurement and what we would naively expect to happen, and how do you bridge in this gap? And logically, you have two possibilities. One is to invoke new ingredients in your model. The other one is to tweak the model. And this is very much the theme of this what I'm trying to get across. But in fact, we knew about the dark matter problem since the days of Zwicky. He looked at class of galaxies. This is a class of galaxies taken with Hubble Space Telescope in a project called CLASH, in which I'm also involved. Beautiful galaxies. He looked at the motions of those galaxies, and using the Viral theorem, again, he inferred that the mass that has to hold this structure together is far bigger than what you actually measure. Since then, we have new techniques such as X-ray, for example, Zeldovich effect, and others. But perhaps the most remarkable one is gravitational lensing, which of course goes back to Einstein's ideas that actually, although the object is there, we see it deflected by the curvature, by the massive object, or by the curvature of space-time. And this leads to all these funny features there, which we call arcs and arclets. Look, even in this one, see the bending. It got even bended by those two massive halos, if indeed they are massive halos. So it's a beautiful subject, a very active area. In fact, Priya is one of the leaders in this field. But actually, the result is about the same as what Zwicky told us, that if we interpret it within the conventional model, there's lots of dark matter. Okay, let's speed up a bit. What was obviously a major turning point is the usage of supernovae to tell us distances. This is actually a supernova. You can see it there in the galaxy M82. And this was actually discovered in January in our teaching observatory, which is located in the worst possible place on Earth for observational cosmology. It's the lights of North London and all that, clouds, of course. But we like to think that by training students there, then when they move on to run big observatories, they can easily detect quasars and supernova at much higher redshifts. And indeed, we have some alumni who've made it. So it's interesting to show that these are real events. Okay, it's real events. And then nature has been kind enough, or at least we would like to think it's been kind enough, that we can take data from supernova like this plus many others that are now over 700 or so, and actually plot their flux after some corrections. Some of them has to be said are empirical, against the redshift, and get this beautiful so-called Hubble diagram. And this line actually suggests that the universe is accelerating, and that's won leaders of those two teams the Nobel Prize in 2011, that actually the supernovae look dimmer than you would expect had you observed them in a universe without something like a cosmological constant. So although the Nobel Prize Committee was very careful to say the prize is for discovering the acceleration of the universe, they didn't tell us what is causing this acceleration. Again, it's very much related to the theme of this talk. What do you do when there's discrepancy? So moving on, nature has been kind enough for a second time by producing rulers on the sky. This has to do with an effect called baryonic acoustic oscillations, which one can explain quite easily, almost in terms of, you can almost use kind of simple classical physics to actually explain why you'd get these oscillations as a result of the photons, baryons oscillating in the deep potential wells. And you can actually see those features in the cosmic microwave background. If you take a map and do it Fourier transform, you'll see a peak. And you can also see it in galaxy large-scale structure. In fact, it was detected by 2DF galaxy survey, in which I also spent about a decade with 30 other British and Australian astronomers, and the Sloan Digital Sky Survey. And this year's the show prize was given actually to 3 colleagues who led the efforts to actually detect those. So the nice thing, we have those 2 rulers here, and we can do cosmology, we can do geometry, just like Mr. Euclid. Okay, and that's actually, we like to do Fourier transform. For those who wonder how we go from just dots on the sky, we Fourier transform the sky. And this is the wave number, and you can see those oscillations in full glory. In real space, there's just a peak at about 150 megaparsec, H inverse megaparsec to be precise. You do the Fourier transform, you see all those wiggles there. And then there's a machinery of fitting data to a model. We are very much working on the frame of a Bayesian inference. So we also assign priors, and we have to worry about systematics. But state of the art from a project called BOSS is that the equation of state parameter is very close to -1, and that means a cosmological constant, and that the universe is flat. So this is very much a state of the art. It doesn't mean that we cannot maybe have other alternatives to that. But when you assume that, the data seem to agree with that. Now, this was again supported if you take the Planck data. We heard earlier a very nice talk about the CMB. This is WMAP. This is Planck, same universe. As commented on, we have only one, but we can observe it at different resolutions. And this is the mix of composition of matter and energy at the present epoch, before Planck and after Planck. As you see in the big picture, not much change, 5% ordinary matter, baryonic matter, 25% or so dark matter, and let's call it 70% dark energy. And this was this paradigm shift. When I was a PhD student in Cambridge in late 80s, it was 5% here, but all the rest was blue. There was assumed to be zero dark energy. I feel lucky to actually experience paradigm shift, which unfortunately our students have not experienced yet. And that's a very bizarre situation living with those components. As John Barrow commented earlier, there's so many possible universes. Why is it we've ended up with this one? What does it do? Again, this is for the non-specialists. If this is time and this is density, that's the cosmological constant. It's just a constant with time and space, while the matter and radiation get diluted as the universe expands. So here is this very strange coincidence that we happen to live at a time that the universe is accelerating, right? Had we lived at this epoch, it would have been quite different. So it's only recently that the universe became dark energy dominated and accelerating at slightly different periods, but essentially it's very close to the present epoch. Okay, just for those who don't look at it every day, cosmologies are quite good in parameterizing ignorance. So we've taken that equation, pressure to density, which we call W. When W is -1, this is Einstein's cosmological constant, and here is just a Taylor expansion of that, A being the scale factor. And then funding agencies want a number. So the community had to come up with a simple language which captures the efficiency of a survey, and that's the inverse of those, the product of those error bars in those 2 parameters, or a slightly different version of that, so-called pivot redshift. But basically what it is, and I'll show examples, it's the size of an ellipse. In fact, you've seen some of it before. You try with each measurement to minimize that size the size of that ellipse. And if you manage to prove that your ellipse is smaller by a factor of 3 relative to the previous generation, then you can win the tens and billions of dollars. So it's kind of interesting capturing a deep physical question through a statistical measure, which then translates into the policy making and money by this simple equation. I'm not saying it in a cynical way. I think we're very fortunate to actually develop that language. And it seems to work, at least for those who got the money. So what is dark energy? By this time, you probably, those who don't think about it every day, probably a bit confused. Well, the short answer, we don't know. We know the universe is accelerating. At least the Nobel Prize Committee is convinced by that. Could be still systematics mimic that. It could be that we just live in a lambda cold dark matter universe with equation of set of -1. It could be that this dynamical field evolves with time. It could be that we need to modify gravity. Maybe we live in an inhomogeneous universe. Multiverse was mentioned here a number of times. There's some conference I go to where multiverse is not allowed to be mentioned. So it's refreshing to be in a place where it's very legitimate to talk about it. Because the point is, how come we ended up with this strange menu of 5%, 25%, 70% for baryons, dark matter, dark energy? Maybe we're out of many. Or something else. The Planck press release through ESO came up with a sentence which I don't understand or don't agree with, that it's an almost perfect universe. I think it's a bizarre universe. And I agree more with the New York Times version, that it's a simple but strange universe. The history is well known. I think we haven't heard, there was no mention, and I hope some of the more theoretically inclined speakers will comment that after all, particle physicists tell us that, you know, vacuum energy should be 10 to the power of 120 larger than what we observe today. There is this interesting question that Einstein put the lambda on the left-hand side, and then there's this, you know, sophisticated operation. Even my 5-year-old daughter would agree with that you can put it on the right-hand side. But then it changes completely the story, okay? So I want to emphasize that, and that's where I feel a bit stuck. You know, we do all this hard work, and we come up with all these contours, and we tell you W is -1, but we still don't know, really, if this is a tweak to gravity, or every centimeter cube in this room has got a bit of dark energy, right? So that's what I want to emphasize, where I feel stuck, and maybe some higher level thinking could be helpful. And also, why is it that at present time, why is it the universe accelerating now? Why is it that matter and dark energy are so similar to it in order of magnitude? So I want just to talk about paradigm shifts. And this is actually a couple of papers I did with a student, Lucy Calder, shown there. I just want to kind of document that evolution of ideas, because, you know, we're talking here about ideas. The data change all the time. I think it was Francis Crick who allegedly said that if the model agrees with the data point at a given time, most probably it's the wrong model, because at some point data points will change. So we have to be prepared, you know, for that paradigm shift. And what I want to emphasize that, of course, lambda is an older, much further history, which goes to Einstein trying to get a static universe and so on. But even, you know, 84, Peebles advocated lambda. Statio saw it in the APM galaxy survey. For my sins, so in a postdoc, I had the privilege of collaborating with Joel and Martin Rees and Per Lilia, and we actually speculated about what lambda can do, and then it came in baryon fraction and the case for adding it in other papers. So I'd like to say, you know, it's great what the supernova team have done, is great, and it's direct detection, but I think all this earlier work paved the way for them to prepare the ground for that huge change. This is the Peebles paper where he says the data agree reasonably well with omega. He means here omega matter of 0.2 and a flat universe. So he points out you can live with inflation, you can have zero curvature, and all you have to do is put something else. If you got 0.2 in matter, just do 1 minus 0.2 and you get 0.8. That's lambda. And here is the Statio et al. Paper based on the APM. Now, this is kind of intriguing. again, it appears in those two semi-popular articles with Calder, which you can find, for example, on my website. I think I first came across it in a book by John Barrow, and then discussions with Lyndon Bell. You know, usually we think lambda goes back to Einstein, okay? But actually, it turns out Newton talked about it in Principia, and he proposed two laws. One is 1/r², one is linear. He made a terrible mistake not calling the constant lambda/3, and then dismissing it altogether because it wasn't good for the solar system. Maybe I can explain, if people are interested over coffee, why he came up with this. It's all in Principia, and allegedly it's the place in the Principia where he allowed himself to be most emotional in the whole of Principia. So he obviously got excited by it. I find myself just last year actually using that equation, that very equation, to explain the motion of the local group, the Andromeda and the Milky Way. So there's this time, you know, one of the methods measuring the mass of the Milky Way is to look at assume Andromeda, Milky Way star same point, the universe expands and they fall towards each other. It's called the timing argument, which has been worked out by Kahn, Volter, Lind, and Bell. Strangely enough, it was somewhat overlooked, although it appears in the literature, but somewhat overlooked, that if there is lambda there, it makes a big difference. So, you know, usually we think about this, we have to see lambda, we have to go to hundreds of megaparsec. What I argue that in the local group, lambda makes a big difference. It gives you a big push. As a result of that, the mass you derive is 13% higher. It's also an interesting comment to make that the local group seems quite unusual. We're doing more work on this, looking at simulations. It's quite unusual by being so isolated, if you like more anthropic principle reasoning. It's very unusual being so isolated, so you can apply this argument. But I find it quite mind-boggling that it's 13% effect. So this brings me to the key point of this talk, okay, that really in both the rotation curves with the massive clusters and now with dark energy, we're stuck with that situation. There are data. Let's assume for now that the data are perfect. They won't change. Let's assume. There's a model at a given time. There's a gap. What do you do? I find that quite interesting, you know, that really we see that in the solar system because Neptune was discovered 1846. It was predicted to be there because of the unexplained motion of Uranus. At the same time, there was actually the problem of Mercury's precession. In fact, it was proposed to put a planet there called Vulcan, which was never found. Instead, the solution comes through modifying the underlying model at the time. I think we are in that situation. These are, by the way, I don't want to get dispute who was the first to predict Neptune, whether it's Leverrier or Adams. It's a French-British debate. There are probably people more competent than me to address it, but it's kind of I find it kind of fascinating. This led me, I mentioned it as a parenthetical remark in a talk, and I was then approached by Michela Massimi, who is a philosopher of science, previously UCL, and now at University of Edinburgh, and we ended up looking at it and writing, again, semi-popular article in Astronomy and Geophysics. It's in June, the June issue, also on my website. And the key point I want to make, again, this is the main theme of this talk, that you have to go for either new entity or new theory. So with Neptune, we went for a new entity. There was, I found, actually, this was became a surprise, I don't know if it's well known, that Bessel tried to come up with an astrophysical solution to the problem. He said maybe each planet is a bit different. We would call it today gastrophysics, you know, in the galaxy formation conferences. While Mercury orbit, the idea of having Vulcan was thrown away. So I put in brackets ideas that didn't work, and GR solved it. One can also give similar example about neutrinos. But it's really, with galaxy rotation curves and accelerating universe, we are still stuck. We still don't know if it's a new entity or new theory. And that's what I'd like to convey, and maybe to see whether, you know, the philosophers in the audience could give us some guidance. With Michela's help, we looked at some ideas, of course, in the philosophy of science. So Karl Popper, basically, he looked at Adams and Leverrier as they attempted to shelter Newton's theory, okay? So it's like Neptune was predicted and discovered as a way of sheltering Newton. That's one point of view. Lakatos, on the other hand, thought of it a bit more broadly, saying there's a research program which involves a hard core and protective belts. I like that concept. So, you like to keep what you like, but then you allow a little bit of fuzziness there, and you add a bit of, just another planet, save the theory. Pierre Duhem talked about scientists follow their good sense when facing such dilemmas. Now, personally, as a humble, just practitioner, I can relate most to that, although it was said in 1906 that we follow our good sense. I think it's quite interesting to see whether we could benefit from that experience in thinking about dark energy. So, I'm basically trying to say here is that we are presenting you with dilemmas we have as practitioners of the field. It's interesting to see whether we might give you some material to write papers on philosophy of science, but could you give us some tools to think about this problem? And could this reasoning can equally be applied to dark energy and dark matter? We'll speed up a bit. Some sociological remarks. Are we talking too much to each other? So some people in the audience, I can tell, lived at the time of the Cold War. And it's actually led to two different models of the universe. Hot dark matter by the Zeldovich school, cold dark matter by the Western school. Actually, hot dark matter does exist. It's a massive neutrinos. Cold dark matter probably also exists. There's something quite healthy about having two schools of thought who could not communicate, or at least could not communicate effectively with each other, leading to two ideas. Well, I don't propose a new Cold War, although it may well happen soon. But maybe we can find on a more peaceful means, for example, to fund groups of scientists who think outside the box. Although I am very much in the big science business, it's a very good business, so to speak. You can really run a program and have resources, but maybe that's important to create that kind of diversity. So a lot is going on. Okay, a lot is going on. These are projects, only a subset of projects. Red means spectroscopic surveys, blue means imaging surveys. You see, we are like particle physicists now. We plan ahead all the way to 2031 and beyond. There are billions of dollars or euros spent, but the good news, this will create samples of billions of galaxies, so it's $1 per galaxy, which is an absolute bargain. I hope you're convinced if you're supporting this. When I moved from Cambridge to UCL to head the group there, Joe, I think, knows the history of that. We decided to go for the Dark Energy Survey, which was a kind of a successor of Sloan, together with Fermilab and other institutions. There are now 25 institutions, 6 countries. It's a huge commitment. I want just to convey it to the people who, even within cosmology, who don't practice, huge commitment when you decide to go for something like this. The optical corrector was actually built in our basement with help from the UK funding agency, STFC. The idea is to do different techniques, and I alluded to them, such as lensing and large-scale structure, supernova. It will produce 200 million, catalog of 200 million galaxies, 4,000 supernovae, lots of synergy, for example, with South Pole Telescope. It's working on this telescope in Chile. It's actually working. We are now doing the second season. So the purpose of that is just to relate this kind of more philosophical question to what's actually happening on the ground. This is the collaboration. You see the camera. It's one of the largest cameras in the world. It's about 70 times larger than the camera on your iPhone. I haven't checked iPhone 6, but I think it's still bigger than that. Here is the array of CCDs, and you can see beautifully, this is Fornex cluster. You can see a galaxy there. And there is science coming out of it. You've seen that diagram. This is from Hubble Space Telescope. And you can use the basic lensing relation. Here's the observer. There's a lump of matter, unseen. And here is a distorted image. And this connects cosmological distances to the mass of the deflector. So you can learn about both. And this is just an example. It's just like optical lensing. And you can see, if you put the candle at the right place, you'll see this, what we call in the gravitational lensing Einstein ring, and if not, you'll see those arcs. And indeed, we see them in the Dark Energy Survey, although it's from the ground. It's not as beautiful as HST, but we are going to observe 5,000 square degrees. And there's already science coming out of it. In fact, there are 3 papers. There's papers on AstroPH, and this is one of them. And the dots are galaxies, and the contours are actually dark matter. These are contours of dark matter derived from lensing, assuming general relativity. You may come and ask me, what if you change this model? But within general relativity, it's quite remarkable that the light and mass are somehow related, and if you can even go and trace some filaments. So this is not the end of the story. This is yet another project called DESI. Please don't confuse DES with DESI. This is Spectroscopic Survey. If you've seen BOSS with the beautiful wiggles, this one is 10 times better than BOSS in terms of numbers of galaxies and error bars. In fact, it just had what's called CD1 DOE review in Berkeley, and it passed it successfully just this week. And then there's going to be an interesting play, because I alluded to modifications to gravity. Now, what is non-GR? Well, what's a non-elephant? You can try many things, but this seems to be a very popular parameterization. I can't see from here. 5, thank you. I'm all right. You can see this parameterization of allowing the metric to have 2 potentials, which are not the same. Usually we assume they're the same. And in fact, the cosmic shear is sensitive to the sum of them. Peculiar velocities are sensitive to the temporal one. By combining the 2, we can bring it together. And this is a work in our group led by Donica Kirk, a postdoc of mine, where we really show, I won't bore you with all the ellipses, but this is this WA, W0. And if you combine imaging and spectroscopy, you can constrain that, as well as constraining parameters of this modified gravity. So it's all very nice that I think we might be able to really say something more constructive on these 2 options. Is it a modification of gravity or a new ingredient? In passing, I'll mention, because maybe there are people with particle physics interest, that we can also use the data to constrain neutrino mass. At the moment, the upper limit, even after Planck and from work our group has done and so on, is only 0.3 eV on the sum of 3 neutrinos. If you combine DES one day with Planck, you can get to 0.1, compare with Catherine. And there are moments I'm glad to be an astronomer when I see that, but depends on your taste. That's the Catherine experiment on its way. What's very important here, we heard about the question, how many cosmological parameters are there? 6 or 9 or 12? We're actually also stuck on the practical level, where again, we feel some guidance on methodology is useful. How broad is the cosmological model we have? You get different answers if you assume neutrino mass or not. There's lots of astrophysical uncertainties, such as galaxy biasing, for example. Dust in supernovae, intrinsic alignment, weak lensing. Apologies, it's a bit of a jargon to the non-astrophysicists, but the point is there's lots of astrophysics to understand. And finally, we have to worry about instrumentation issues such as image quality, photometric redshift, and so on. What I want to say, when I heard the earlier talks today, people talking about 6 parameters, I said, wow, this is so wonderful. We really have to struggle with hundreds of parameters. So although the abstract at the end says we found those 6 parameters, actually what goes into it, consciously or unconsciously, subconsciously, actually hundreds of assumptions, and we call them nuisance parameters, and I think we desperately need a methodology there. I don't know if it's high-level philosophy, but we do need some thinking there, and we have some ideas which I can share with you. Bayes' theorem is very important. The community became Bayesian. Again, this was also a paradigm shift. The 2 key points, I would say, attention to priors. It's very, very important what you assume as priors. And also, there's this glorified denominator, which is called now evidence, which you can use for model selection. I mean, we should be able to say whether model A is better than model B. So there's a lot of that going on, which is, again, if you like, under this area of reasoning and thinking. Finally, I'm nearly there, Priya. just another point, I've been involved in 2DF, there's 30 collaborators, there's a number of collaborators. Number of collaborators, 30. Now I'm in Dark Energy Survey. When we started, it was a small team 10 years ago, now it's 300. Planck, I believe it's 400, correct? Euclid, 1,000. LHC, 4,000. This meeting I went to, there were 600. I'm glad to see that this meeting was properly designed to keep the numbers low. And what I'd like to emphasize here is at some point, and as I said, I'm coordinating the science program, it's 12 working groups and many telecons and so on. You start thinking, with how many people can you communicate? And I was quite pleased to discover this piece of literature by Dunbar, who is an anthropologist, behavioral anthropologist in Oxford, so some of you may know him. And a while ago, he came up, he has articles and books about this. He thinks that it's 150 is sort of the maximum. This is a cognitive limit. It's the number of people with whom we can actually interact effectively. And I have to say, from my own experience, it's about right. It's when you start crossing that level that you feel, you can only talk to the chair of a working group. You can't already talk to all of them, If you think about administration in your university, you'll probably reach the same conclusion. It's all interesting. It's even more interesting because he did it by scaling the brain of primates. He looked at the brain size, or the active part of the brain, relative number of, versus the number of mates, and then he extrapolated and got this 150. I know it sounds a bit of science fiction, but quite interesting. There are plots. They look linear, by the way. So it's all interesting. So this meeting is absolutely fine. It's below 150, I think. So we expect lots of interaction, we'll be able to talk to each other. But of course, I don't want to say we cannot spread our knowledge beyond. And so that's the team at the back there, with this videoing and all the articles for the book. So we're doing our bit in the UK. Impact in capital A is a big thing. How do you spread it? And we're planning a multi-author desk book. And this is, we support artists in residence. So this is, if you haven't seen Dark Energy, come to our observatory. And this is the Marie Kau's image of that. We have an anthropology study of DES. In other words, we're looking at the collaboration as a system. And these other aspects of thinking about paradigm shifts. That's last slide, Priya. Discussion. I think, what we can report is the lambda CDM with this W being -1 cosmological constant is actually supported by the latest data, okay? So nobody at the moment can rule it out, throw it away, but modified gravity and variation of W are still possible. To me, this is the main thing that bothers me as a practitioner. Do we need new entities like Neptune, or do we need to tweak the theory, as in the case of Mercury? I think it's fair to say cosmology is undergoing an industrial revolution. With pros and cons, it's fun working in a big collaboration, but how do you keep communication effective? And is the sum of intellect, actually generate new science? And of course, I'm very curious to know, after experiencing one paradigm shift, fortunately, what will be the next paradigm shift? And I'll stop here. Thank you.
Thanks. So now for questions.
Thank you. Very nice talk. Can you go to slide 12? In fact, I have 3 very brief comments. I don't know if I will. So while you go there, one is super quick. At slide 15, you said the particle physicists say that the cosmological constant.
Is this the one you wanted?
Yeah.
Yeah. Okay.
So let me start with the other one. In the 2 slides later, you say that the particle physicist says that cosmological constants will be 10 to the 120.
Yeah.
So my comment is just don't believe them. They're obviously wrong.
Fine. Well, let them defend it. Okay.
Right. So about this one, the horizontal axis is a logarithmic axis.
Yeah.
Now, if you throw a dice many times and you plot the result in a logarithmic axis, they are precisely condensated on the right-hand side like that. So you get that your dice is very biased for mysterious reasons, and it always falls on the right-hand side. So be very careful about thinking that there is a
Well,
peculiar
I'm happy to
coincidence
follow
there.
up it later, and it's down to frequencies, Bayesian, and all that. I'm happy to, let's discuss it later.
Okay.
It's a valid comment, but I'd like to
Yeah, I
discuss
just
in
wanted
depth.
to
Yeah.
raise a flag word.
Yeah, yeah.
And the last comment is also super short. I very much appreciate that both for dark energy and dark matter, you say there is a solution with a new thing and a solution with a new theory. But I would like to point out that the two cases are very different. I'm a theoretician, of course. Very different as regard as the theory. Because there are, of course, twinkling of generativity with dark matter, but from the point of view of a theoretician, they just don't work very well. In fact, they work very, very bad. You can sort of try, but they don't. On the other hand, as far as dark energy is concerned, there's no twinkling whatsoever. It's just the most natural version of generativity for theoreticians is the one that works.
As long as it's not 10 to the 120.
Don't believe them.
Right, okay.
That's why I said.
Okay, thank you.
Thank you. Thanks, Olaf. Yeah, just I disagree with your analogy. Great fun, but I disagree with your analogy on the use of MOND to, let's say, account for dark components of the universe and general relativity in the case of Mercury, both historically and philosophically. First of all, historically, as you well know, general relativity was proposed to give us a generalized version of special relativity that could include gravity. It's got nothing to do with Mercury or any other planets. Einstein is always happy to use postdictions or predictions, but he would see that as just a phenomenon here, a phenomenon that. It was not the motivation, whereas here it's the other way around. So that's the first thing. But also philosophically, much more seriously, that there's this narrative all the time now that somehow I see at the popular level that dark matter and dark energy are these quick fixes, you know. I mean, in the case of dark matter, once somebody has raised the question that why are you assuming that all the okay, we see matter which gravitates and which interacts with EM, but that doesn't mean that all matter gravitates, that all matter will interact with the electromagnetic force. There's no reason to make that assumption unless you've got some deep connection between the gravitational interaction and the electromagnetic interaction. So I would say it's one less assumption about the universe, far from a quick fix. And then, as Carlos said, the same comes to the cosmological constant. I mean, I think everybody realizes now, it's fixing it to a particular value was the problem, whether you set it to 0 or in Einstein's static universe, you set it to a thing. The constant itself occurs as a natural thing, and it shouldn't be confused with the whole thing of the vacuum energy or the particle version, etc., etc. But there's no, why would you exclude it? And again, I would say that's one less assumption of the universe to leave the cosmological constant. Can I just finish by saying, I mean, it wasn't just Jim Peebles, seen as Sean Carroll is here. It's no coincidence that people like Sean Carroll and Lawrence Krauss and lots of theoreticians had included this all along. They didn't subtly start talking about the cosmological constant when the acceleration was observed.
Well, only comment. I don't disagree with what you say about the first comment. I think of course, one gets into those entity versus new theory sometimes in different routes. But about the comment of how natural or not natural lambda, I can only just be a witness. Late 80s, if you spoke about lambda in the mid 80s, people would think you're completely wasting your time. No. So there are actually, it's a given time things. What sounds natural, it's a matter of taste, and it changes with time.
So, James Hartle, I noticed you didn't mention the bullet clusters and the baby bullets and the deflection of light on galactic scales by comparing masses from lensing and stellar statistics at their core. Are they not relevant for somehow the scales you're considering? They seem to support GR.
Yeah, that's just due to lack of time, not going through everything.
Okay, thanks.
Bullet cluster is an interesting system where you can see the baryons and dark matter being separate. Would be nice to have more example of those. I'm sure big, wide field. And some would. I mean, I know that people in the Tevis camp. Fine. Okay.
Simon Saunders. I just wondered, your list of possible explanations for the cosmological constant or dark energy, you didn't include zero-point energy. I just wondered, is there a reason for that? So on that long list of you had several candidates, but there was no zero-point energy. I just wondered why.
Okay, I think maybe I clumped it as a part of kind of vacuum energy or scalar fields, but this could also go as another bullet point.
All right. Okay.
Final question? If not, let's thank all for everyone.
Sure.